Hi everyone, I'm Yuan, and the authors are unable to attend due to the visa issues, so it's my pleasure here to present this paper on their behalf. So the title of this paper is Instruction Backdoor Attacks Against Customized Large Language Models. So this is a joint work of the University of Electronic Science and Technology of China and also CISPA and NetApp. So customized large language models, such as GPTs from OpenAI, are increasingly popular. So these models enable the creation of language models through natural language prompts without the need of coding. And this makes them deploy with a very low cost for various applications. So here is an example in GPTs. So you can see that in the instruction field, a builder can create a joke bot using only natural language prompts. And once the GPT is created, it can be published in GPT store. So then the users can access it or further call interfaces for secondary development. So given their widespread use, so it's crucial to ensure that the safety of these large language model applications. And current safety measures focus on privacy and content safety. So for privacy, users' chat histories are not shared with the builders, and also the builders do not disclose instructions to users. And on the safety front, OpenAI has adopted systems to prevent users from sharing harmful GPTs, and including those that involve like fraud activity, hateful content, or audience segments. So despite these measures, an important question still remains. Is it truly safe to integrate customized large language models such as GPTs? So one significant threat is that the backdoor attacks. So attackers implant a hidden backdoor into the victim model by poisoning the training dataset or manipulating the training process. And at the test time, the backdoor model behaves correctly on benign samples, but exhibit backdoor behaviors on trigger samples. So for example, the original sentence can be modified by adding a specific trigger, such as say if, and to activate the backdoor. So our intuition is that the powerful instruction following capability of large language models may make them susceptible to backdoor attacks by simply modifying the instructions given to the model. So attackers can inject backdoors, avoiding the model tooling process. And next, we introduce our instruction backdoor attacks. So here is the attack scenario. The attacker creates and publishes custom version of large language models by involving backdoor instructions into the prompt. And then the developer integrates the backdoor large language models and releases their applications. And once the model is released, the attacker can attack these applications. So in our threat model, the attacker does not control the back-end large language model, but it can manipulate the instructions. And the goal is to design backdoor instructions and trigger specific behaviors without affecting the model's overall utility. And we propose a universal inference process for backdoor attacks, which include actually 5 steps. So the first step is the task instruction design, which is used to describe the target task. And for the backdoor instruction design, we show that the details of our word level, syntax level, and the semantics level attacks in the next slide. So we also provide some demonstrations to make sure the output format, and then we combine the 3 components together to generate the backdoor prompt. And finally, we feed the prompt to the large language model to generate the results. So we achieve 3 types of backdoor instructions. The first one is a word level backdoor. So we use a specific word to trigger the backdoor. And the second one is the syntax level backdoor. We use a specific syntax as the trigger. And so here we make all the sentence starts with a subordinary conjunction to be classified as the target label. And the last one is the semantic level backdoor. So we do not modify the sentence, but we use the semantic as the trigger. So for example, all the sentence related to the topic of a word should be classified as positive sentiment. And these varying levels of backdoor attacks ensure that the attacks are flexible with progress stealthiness. So here's the evaluation results. So for evaluation, we use 5 benchmark datasets and 6 popular large language models. And here is the results of the word level and the syntax level attacks. So most of the models can achieve an attack success rate higher than 90%. And besides, we can observe that GPT 3.5, GPT 4, and also Cloud 3 can achieve higher attack success rate. And this is due to that they're more powerful instruction following ability. So here is the results of the semantic level attack, which is very similar to the word level and the syntax level. So this attack results demonstrate that the robustness and effectiveness of our attacks. And we also conduct some evaluation study to understand the impact of a lot of factors. So we conclude our key findings here. So if you are interested in more details, please check our paper. So for the word level attack, a single word trigger is generally enough to conduct this kind of backdoor attack. And a trick here is that the trigger is actually better to be inserted into the beginning or the end of the sentence. And the position of backdoor instructions also play a role, but it has limited impact on the overall attack performance. And besides, involving poisoning example in a demonstration it can definitely lower both the attack success rate and the accuracy. And when we talk about the demonstration, so our results show that the for clean example is enough to guide the language model for desired performance. And further, we explore the stealthiness and the detection of these attacks. So using ANIA for trigger detection, we found that syntax level attack can achieve a higher level of stealthiness than the word level attack. And in semantic level attack, the sentences are they are not modified, so the trigger detection is not applicable. And we also extend these attacks to generative tasks. So these results show that the instruction backdoor attacks is also effective on generative tasks. And we also compare our results with in-context learning backdoor attacks, which modify the examples to inject the backdoor without fine-tuning or coding. So our attacks are simpler, but more effective. And for complex tasks, so straightforward backdoor instructions can replace the need for detailed examples and making the attack easier to be executed. So then we talk about some practical scenarios. So in these kinds of practical scenarios, embedding backdoor instructions with non-sync prompts can help evade detection. And we test the prompts of varying lengths and find that even with longer prompts, our attacks still remain their performance, showing the practical feasibility. We also care about the defense, so the mitigation part. So to counter the instruction backdoor attacks, we propose 2 defense methods on both the vendor and the user side. So for vendor, they can utilize large language model as a safety checker to detect whether the prompts contain backdoor instructions. And the detection granularity includes the prompt level and the sentence level. So the sentence level detection using GPT 3.5, GPT 4 can both achieve perfect detection success rate. However, such a high false alarm rate makes the detection impractical for real-world use. And also on the user side, injecting a defense instruction before each input can mitigate the impact of backdoor instructions. For example, adding an instruction to ignore any specific instructions and focus only on the main task can be partially effective. So here come to the conclusion of our work. So in this work, we present the first instruction backdoor attacks against the customized large language models, for example, GPTs. And it actually includes 3 levels of attacks with progress stealthiness, like the word level, syntax level, and the semantic level. And our results show that our attacks achieve the desired attack performance without compromising utility. And Our findings also highlight the vulnerability and the potential risks of large model customizing like the GPTs. So yeah, we hope that the robust defense mechanisms can be proposed in the future. So yeah, thanks for listening. So, because I'm not the author of this paper, so feel free to contact them if you have further questions. Yeah, thank you.